You clicked, and the color knew where to go. It filled every nook and cranny. You were 7. Life was good. You didn't question things like this. But under the hood lies an algorithm, like a racist ICE agent, who goes neighbor to neighbor asking, "Are you the same color as me? Are you inside the border?" The algorithm is called breadth first search. And it works. It's just slow. So don't hold your breath. It's the kind of algorithm that takes the stairs. But what if there were an algorithm that took the elevator? That algorithm is the jump flood algorithm. If you've ever touched TouchDesigner, then this is probably the first thing you ever made. The infinite hallway. Nice. And then you move it, and it's still going towards the center. The feedback doesn't know where the rectangle is. Every pixel is just scaling towards the center of UV space. It has no concept of nearest surface. What you actually want is for each pixel to know where is the closest piece of geometry to me and in what direction. That information, nearest surface, distance, direction, is called a distance field. And to build one in real time on a GPU for arbitrary shapes that move or change every frame, you need the jump flood algorithm. Let's set up the problem. You have an image. Some pixels, like you, are special. We call them seeds. Every non-seed pixel needs to answer one question. Which seed is closest to me? And well, you could just check them all. Every pixel measures its distance to every other pixel, checks whether it's a seed, and keeps the closest one. For an HD image, that's about 4 trillion distance checks per frame, which is kinda slow. Okay, so what if pixels just talk to their neighbors?
Hey, the closest seed I know about is over there.
Cool, that's closer than mine. Thanks. Hey, one more thing. Stop talking to my wife.
This is neighbor by neighbor propagation. For a 16 pixel wide image, you need 15 passes. But what if we didn't step one pixel at a time?
It's one small step for man, one giant leap for mankind.
Pass 1. Every pixel looks not at its immediate neighbors, but at pixels half the image width away, in all 8 directions. It asks, who's your closest seed? If any pixel reports a seed closer than what this pixel currently knows, it updates. Pass 2. The jump distance halves. Quarter of the image width this time. Same 8 directions, same question. Pass 3. It halves again. And after just 4 passes, log 2 of the image width, every pixel knows its nearest seed. 4 passes. Not 15, just 4. So what does each pixel actually know after JFA? The blue channel stores the distance to each seed, the how far. The red and green channel store the UV coordinates of the nearest seed, the where. You can also pack an integer ID into the alpha channel if you need to tell seeds apart. By subtracting the UV coordinate and the seed UV coordinate, you get the direction, the which way. Direction, distance, identity. Just from one texture. This algorithm opens the door for a lot of cool things. So I'm gonna show you some fun stuff that you can do with it. For example, Voronoi diagrams, where you draw the borders where 2 regions meet. This results in very nice cellular patterns. Got a black hole in your universe? Don't worry, JFA can patch that bad boy right up. And remember our broken infinite hallway? Well, here's the fix. Run JFA on your seed points and instance geometry centered on these points. Now every pixel has a direction and distance to the nearest point. Use this information to transform your geometry. And now the feedback is local to that geometry. And what if you run JFA on JFA? You get these hairy tendrils that kind of remind me of river deltas. If you know the distance to the nearest surface, you also know how to avoid it. JFA gives you a real-time signed distance field for arbitrary shapes. And you can advect particles by the field and steer them clear from any objects. Something else that Big Cell Tower wants to avoid is knowing how easy this signal propagation effect is. Just multiply the distance field by a big number and feed it through a ramp and a lookup top. And if a signal can propagate, so can a path. Remember the paint fill from earlier? You can use it to solve mazes. JFA can solve mazes too, almost instantaneously, which kind of feels like fast forwarding through a movie. Sometimes it's more fun to watch the slow algorithm and contemplate things. Things like 6 degrees of separation, The idea that any two people on Earth are connected through at most 6 introductions. You know someone who knows someone who knows someone, just 6 hops and you reach anyone alive. JFA works the same way. Every pixel starts knowing almost nothing, just whether it's a seed or not. And through a few rounds of reaching out, not to the pixel next door, but across the image, every pixel knows its nearest seed. Distance, direction, identity. A few questions and talking to your neighbors, that's all it takes to find out where you are and where you belong. Even in a maze.